everybody, welcome to Newton's first law of motion. We're going to be taking a real brief run through of this law as like a recap or a refresh, whatever you want to call it. As we've all heard before, we talked about this in class, but an object in motion will stay in motion at a constant speed, which is the key, and an object at rest will stay at rest unless an unbalanced force acts on it. Basically, objects are lazy. They want to keep doing what they're doing, and the only way to make them change their motion is for a force to act on it. All right. Now, so changing their motion, it's harder for objects that have a lot of mass. So those objects we say have more inertia. And official definition of inertia, tendency of an object to resist changes in its motion. All right, force diagrams, we've talked about these. Basically, we are using them as very simple showcases of all the forces acting on an object. So if we have an object sitting on a table, we have two forces, the weight of the object itself and the force of the table, which is pushing back up, which we call the normal force. Okay, and in this case, the total amount of force in this object is equal to 0. Now, how do we write that? And this is it's not really an equation for Newton's first law, but if you want to attach some sort of equation to Newton's first law, we have the sum of the forces equals 0. And that is, we've talked about that in class, and that's what it looks like. All right, so let's talk about some examples. We just talked about a book on a table. Let's get some others. Let's say you're driving down the road in a car at a constant speed. Maybe you have cruise control on. The force of the engine is certainly making it go forward. So we'll just call that force F sub E, force of the engine. All right, it's kind of maybe an applied force. There's different ways to talk about it. Now, if it's moving at a constant velocity, that means that the forces in the direction of motion have to be balanced. So that means there's other forces acting the opposite way than the engine is pushing it. So what other forces could it be? Well, there's air resistance, there's friction between the road and between the axles and the wheels and things like that. We will just generally label this friction just for simplicity's sake, but when we do that, we have an arrow that is, I don't know if that's the same length, but let me make that the same length, and there we go. You get the idea, and we will call that a frictional force. All right, we're not going to label it specifically right now, but those two cancel out, and net force equals 0. All right. Of course, as well, there will be a weight force and a normal force, so you could add those in if you'd like. All right. Let's talk about the idea of skydiving. If you are skydiving, you reach a speed called terminal velocity. And that is a point, I'll write that down, terminal velocity. That is a point where you stop speeding up. So we know that the acceleration of gravity will speed you up when you fall at 9.8 meters per second every second. But when you hit terminal velocity, when you jump out of an airplane, the wind counteracts the force of gravity. So we have your weight, which is the force of gravity, and we also have the drag from the air. All right, we'll label that D. And when that wind drag equals the force of gravity, then you hit terminal velocity, and you will move at a constant speed while you're falling. You will not speed up anymore. All right, so those are a couple examples. Now, let's look at component forces. We've talked about these as well. All right, and I'll use the example of the sines, which we looked at in class. So if we have, I guess we didn't actually do sines in class, but we looked at hanging masses. I'm going to look at this through a sine. So we have two ropes or cables which are attached to some sort of a sign. Maybe it's a store sign or something, and it's holding up the sign. Now, it should make sense that all the forces holding this sign up are completely balanced, and they equal 0. So therefore, this is absolutely a Newton's first law situation. Let's draw a free body diagram. What forces are acting? Well, we have the weight, of course, which is straight down, and we also have the tension of the two cables. We'll call them T1 and T2. All right. Good. Now, when we talk about component forces, it's just the x and y parts of those. So I'll draw these in here. So here's the vertical component of T2. Here's the horizontal component of T2. Here is the vertical component of T1 and the horizontal component of T1. So I'll label these TX1, TX2. This is, TY1, and this is TY2. Okay, there you go. That looks really messy, but you hopefully get the idea. All right. So what we find out here is that, that's really bad. Let me look at this again. What we find out here is that the two forces here, we can draw it like this too, have the component forces here. So this X force plus this X force have to equal 0. All right. So what we have is TX2 plus TX1 equals 0. All right, and that is the sum of the forces in the x direction. TX1 plus TX2. One is positive, one is negative. They add up to 0. The same thing with the vertical forces. And we have to say that the sum of those forces, sum of the forces in the y direction, also equals 0. Those forces are Ty1 plus Ty2, but we also have the downward force of weight minus the weight force, and that equals 0 as well. All right, we can find the weight by taking mass times the acceleration of gravity, and then from there we can move on. If we know the angles, we can figure the rest out. All right, so there are some examples of component forces, Newton's first law, balanced forces. That's basically the sum of it. Total force equals 0. All right, hope that helped. I'll talk to you.